Hello again. Hopefully you can make this exercise today. We are operating with Psi 4 and we have a Q equivalent to 1. So will there be one of exact order 4? That's actually a question. Like if, oh yes, there will, because 4 divides the order. Good. Then we have to show that chi of 4 and chi 4 of minus 1 in this case. All right. Now, when q is equivalent to 1, then there is a square root minus 1. And the same 4 is also a square. And now let's take this one first. That's easy, because it just equals 2 over the Jacobi symbol, 2 over q. And if it's 1 or 7, a q equivalent to 1 or 7 modulo 8, then it's plus 1 and minus 1 if it's 3 or 5 modulo 8. And now in our case it's 1 or 5. So if it's 1 modulo 8, then it's plus 1, and if it's 5 modulo 8, it's minus 1. I believe that was what we should show about chi 4 of 4. And then chi 4 of minus 1. Now how about chi 4? We have chi 4 squared equals chi 4 of minus 1 squared, which is chi 4 of unity, which gives unity. So it's either plus minus 1. Of course, we know in terms of the, no, we don't know in terms of the generator where the square root of minus 1 is. Or could we actually say something about that? I have no idea how to go further than this. That calls for a break. It just occurred to me, if we make the map into the additive number group, then we might be able to take the square root of 1 and minus 1. So the multiple group here of FQ is isomorphic with the number group of Q minus 1 elements with addition, and the unit element, of course, maps to the unit element there. So if we first take Q equals to 5, equivalent to 5 modulo 8, n plus 5, then our group is set modulo 8n plus 4 times z, and then a square root of 0 is 4n plus 2, and it has a square root as well, 2n plus 1. So this guy maps to minus 1. This guy maps to, no, this guy's plus 1, this guy to minus 1, and this is square root minus 1. And of course the other guy, 6n plus 3, is another square root of minus 1. There are 2. But there's no square root to this guy. And that means that in this case, chi4 of minus 1 equals minus 1. Was that what we should show? Oh God. Then let's see B. Q equals 4n plus 1. So we operate with set. Oh, that's modulo 8n set. So taking square roots, 0 comes from 4n, so that's 1, and minus 1 comes from plus minus 2n, that's square root minus 1, comes from, then we have 4 fourth roots, plus minus n and plus minus 3n. So we have a fourth root. And that means that chi4 of minus 1 equals, here it's the upper case, it's plus 1, and in the lower case it's minus 1. And therefore we conclude that chi4 of minus 4 equals plus unity. Right, That was what we had to show.